All right, this is basically going to be one example that talks about how to find complex values in AC circuits. We're going to actually look at probably one of the simpler circuits that we've dealt with in here, but we're going to go through all the possible calculations you might have when dealing with AC power circuits. So, notice this is a very simple series circuit with two impedances. Z1 is 2 minus J1 ohms, and Z2 is 1 plus J5 ohms, and the source voltage is 60 volts at an angle of 0. And note that this is an RMS voltage, so this has been declared at the beginning, which means that any calculations you make with this voltage when you find the current will already be RMS. So anytime we make calculations, we're going to use the effective values of voltage and current because we already know what they are. So, step by step, we're going to go through this process. First of all, we're going to find the total impedance. This is a series circuit. This shouldn't be any difficulty. We are going to note, and this is usually my practice, is I usually find the polar values of each impedance just so I know what they are. I just go ahead and change them and write them down just so if in case I need them I know. And in order to find the impedance, all we're going to do is add Z1 plus Z2, and when we do that we get 3 plus J4 ohms. And again, I'm going to find the polar value of that because I think I'm going to need it later, so I do have that calculated. Also, we take a note that the positive phase angle here means that the net impedance is inductive. That may be important later. It actually is important, but it's kind of a clue as to what's going on. So the system is an inductive system going into this. Now, to find the current, well, we know the voltage, we know the total impedance, so we're just going to take the total voltage and divide by the total impedance, and we can take 60 divided by 5, and that will give us 12 for the amp value. And then for the phase angle, we're just going to take an angle of 0 for voltage and subtract the phase angle of the impedance, and that gives us minus 53.13 degrees. And again, the magnitude of the current is already RMS because the voltage that we used for that calculation was RMS. So that is actually 12 volt current, or 12 amps RMS. So far so good, nothing too difficult. Now, we're going to find the total complex power supplied by the source. We don't usually use in these calculations, we don't use the passive sign convention so much because we're really looking at power supplied and power delivered. So we just call AC power supplied, and we don't worry about changing the current direction. So don't worry about that for AC power. We did that for DC, not going to do that for AC. So, in order to find that value, we just take V effective, I effective, at an angle of their phase difference. So the effective values of voltage and current are 60 times 12, and that gives us 720 for the magnitude. And then for the phase angle, we take theta minus phi. So theta would be the phase angle for the voltage, and phi would be the phase angle for the current. And when we take 0 minus negative 53.13, we get a positive phase angle. This positive phase angle indicates the power factor is lagging. Now, you know that that phase angle came from the impedance, and the impedance was inductive. So having a positive phase angle for either the impedance or for the complex power will indicate that the power factor is lagging. So there's actually two ways that you can kind of determine that, and that's where we determine the leading and lagging part. There's no other calculation we do. We just look at the sign on the phase angle for the complex power, and if it's positive, then the power factor is lagging. If it's negative, the power factor is leading. So we just get that clue from the complex power. Now, the next part asks us to find the total real and reactive power supplied by the source. Well, we know the complex power in polar form, so all we're going to do is change that to rectangular form, and when we do that, we get the real and reactive values already. So all you have to do is change that complex polar number to a rectangular number, And then we know the real and reactive values, that the total power, the total real usable power supplied is 432 watts, and the total reactive power is J576 volt amps reactive. Next, we want the power factor of the system, including leading or lagging. Well, we already determined it was lagging. And there are, given what we know, two different ways to do this. We can get the magnitude of the complex power, which will give us the apparent power, and we can calculate power factor by taking the real power divided by the apparent power, which would give us 432 over 720, which equals 0.6, and we already determined that that was lagging. So that would be one way to find it. The other way would be to take the cosine of 53.13. And when we do that, we also get 0.6, which is good because that's what we're supposed to do. So two different ways to find it, just depends on what you happen to know and what is available to you to make calculations, but either way works just fine to find the power factor. That's not a great power factor, 0.6. It basically means 60% of the energy going into the system is usable power and the rest of it is not. Next, we want the complex power delivered to each impedance. Now, you remember when we dealt with resistors, if we knew the current in a series circuit, we could just use I squared R and find the power. We can't do that. So we're not going to do that to find power. We need to actually find the voltage across each impedance. We can use voltage division for this. If we do that for this first impedance, we can take the impedance Z1 and divide by the total and multiply by the total voltage. And if we take 2.24 divided by 5 times 60, we get 26.88. And then if we take minus 26.56 and we subtract 53.13, we get minus 79.69 degrees volts. So that would be the voltage across Z1. The voltage across Z2, we find the same way. We just take the impedance Z2, divide by the total, multiply by 60, and we get 61.20 at an angle of 25.56 degrees volts. So once we've done that, then we're actually going to use the current also that we found, and the current in each impedance is going to be the same. And for the first impedance, we take the magnitude of the voltage. Again, these are all RMS values because we started out with an RMS value. So the voltage across Z1 and Z2, the magnitudes are already in RMS. So we take the effective value of the magnitude of the voltage in Z1, multiply by the effective value of the magnitude of the current, and multiply those together. We get 322.56, and then we take the phase angle of the voltage of the impedance, and we subtract the phase angle of the current, and we get minus 23.56 degrees volt amps for the complex power delivered to the first impedance. The second impedance, we do the same thing. We take the magnitude of the voltage across the impedance, multiply by the current, adjust the phase angles, and we get 734.4 at an angle of 78.69 volt amps. Now, what we'd like to do, because I always say that there's not really any good way of knowing if your answers are correct or not, but we know what the total power is. We know what the total complex power is. So we could add these two values together and see if we get the total that we got initially. And when we do that, we add those two polar numbers. I didn't bother to convert them to rectangle. And we get 736.79 at an angle of 53.36. Not exactly it, but really, really close. So because it's close, and because these are complex numbers and there's a lot of rounding that goes on, we can assume that that's pretty much correct. That is really close to our value that we calculated, which was 720 at an angle of 53.13 degrees. So the fact that it's a little bit different is because they're complex numbers. We're really not going to worry about that. The next part, we're supposed to find the real and reactive parts delivered to each impedance. So as we did before, we're just going to change each impedance, each complex power to a rectangular form. And when we do that, we get a value for SC1, value for SC2, and that again automatically gives us the power values for each and the reactive values for each. So in each case, we have a power and we have a reactive power, and they both go together. And again, we can go and check and see if these values add up. So we know what the total real power and the total reactive power were, and we're going to go ahead and add up the real powers and reactive powers here. For the real power, we get 439.7 watts. For the reactive power, do have to remember that some of the reactive powers will have a negative J, some a positive J, and you do have to take into account the negative and the positive. And we get J 591.21, and the actual values we had were 432 and J 576. Again, that's close enough. Because we're dealing with complex numbers, it's not ever going to come out exactly unless we do significant rounding and make everything whole numbers, and we don't tend to do that. So this is basically the process that goes into finding complex power. We have to find the voltage and the current anytime we want to know the complex power. If we want to know the real and reactive powers, we just find the rectangular version of the complex power, and that gives us to it. If we want the apparent power, we just take the magnitude of the complex power in polar form, and that's all we need to do.